All right, so for the problem of the day, everybody, this is a little bit tricky to think about. It takes us back to acid-base chemistry, which I know was way back in October, pretty much. But what is a base? Come on, guys. This is like general chemistry questions. What is a base? So you can think of it two ways. You can say, if you're looking at the Bronsted-Lowry definition, you could say it accepts protons. If we're looking at the Lewis definition, what does the Lewis definition say about bases? It donates electrons, right? So now we have to take a look at these two compounds, and we have to look at whether or not the nitrogen or the oxygen can donate electrons. So let's take a look at compound A. And for compound A, there's really only one resonance structure we can draw. And that is where we dump electrons up to that oxygen, giving it a negative charge. That carbon has a positive charge. And if we look at this, the nitrogen lone pair is just hanging out, right? So for compound A, the nitrogen lone pair can act as an electron donor, making it a reasonable base. In this case, it's going to be a better base than an oxygen lone pair, because we know oxygen's more electronegative, oxygen's okay, having a negative charge on it. Nitrogen is less electronegative, making it a better electron donor. It's not going to hold electrons as tightly. All right, now let's compare this to compound B, which is slightly different. So if we look at compound B, we can draw this same resonance structure. Where this oxygen has a negative charge. Whoop, I forgot my double bonds. This carbon has a positive charge, but there's also one additional one. And I'll shrink this down to all right, so this one has additional resonance structures. I'm drawing the main contributors here. Try to shrink this into something that fits in our box. All right, so if we look at the lone pair on nitrogen now, what's it doing? It's delocalizing all the way into this ring, right? If we look over here, it's no longer a lone pair located on nitrogen. It's a lone pair that's a part of the ring system, right? What's special about this ring system? It's aromatic, right? And we said yesterday that aromatic ring systems have a huge amount of stabilization energy. So if we look at the main resonance contributor here, it's actually not the one on the left. It's better to think of this one as the molecule on the right. So most people, if they were to draw this molecule, this would be the better representation, because this would be the major resonance contributor. In this case, there's no lone pair on the nitrogen. It can't act as a base. But the oxygen now has a negative charge, making it a really, really good base, right? It's got lone pairs to spare. It can donate those electrons. It can be a very, very strong base. And so this kind of goes back to the idea that we talked about first term, where we said aromaticity can really change the acidity or basicity of molecules quite a bit, specifically by how a lone pair or a charge can be delocalized through a ring. For the bottom reaction, I'm not going to grade that today, but we're going to go through and do that as an in-class activity so we can practice our synthesis problems a bit more before the exam that's coming up. All right, so let's switch gears back to our notes from yesterday, and I actually wanted to make a correction to something I talked about yesterday. We said yesterday that molecules are aromatic if they have 4n plus 2 pi electrons in a planar conjugated ring system. And then I gave you a bunch of examples, and we counted these pi electrons. And we said that the first one was anti-aromatic because it only had 4 electrons. Same with this one. These two were aromatic because they had 6. The one on the outside that has 8, I was wrong. It's not anti-aromatic. To be anti-aromatic, it technically has to be planar. And this molecule looks kind of funky. It's actually tub-shaped, or if you imagine those double bonds on the side, they're bent up a little bit like that. And because it's not planar, this is just simply not aromatic. It's not anti-aromatic. So I misspoke there. To be anti-aromatic, you must be planar, and you must have 4 pi electrons, or 4n pi electrons. So that was a slight discrepancy I made. And then we went through and we said that all of the positions in the ring need to be usually sp2 or sp3 hybridized to allow for delocalization. If we have an sp3 hybridized carbon, we can't have any resonance going through those positions without violating the octet rule. So these don't exist as aromatic compounds. This is just simply a non-aromatic compound. All right, where things get a little bit interesting is when we take one of these carbon positions and we swap them out for atoms that aren't carbon. And we saw that on the problem of the day a little bit. And so these are called aromatic heterocycles. And basically what a heterocycle is it means you're taking one of those carbon positions and you're swapping it with maybe a nitrogen, maybe an oxygen, maybe a sulfur. Something that's not carbon is being swapped in. And there are some really common ones that we've already seen, actually. Does anybody remember the name of this compound? Pyridine, right? All right, so let's take pyridine. And let's think about those p orbitals that exist on pyridine. And specifically, I'm going to take this and kind of tilt it on its side. So I'm going to have a carbon. This carbon's going to be in front. This carbon's going to be in front. I'm going to have a nitrogen over here. This carbon's back here, back here. Does that make sense? So we're kind of doing a side-on view of pyridine. Then I'm going to go through and I'm going to draw our p orbitals for this. I'll give it a little bit of artistic perspective there. All right, so we've got 3 sets of double bonds in here, right? So I'll highlight these double bonds. We know that they can delocalize. Where's that lone pair? Sticking out 90 degrees, right? So let me actually draw this orbital in a different color just so we can really identify this, and I'll label this a green orbital. And we've got 2 electrons in there. Specifically, the lone pair is in a sp2 orbital. A sp2 orbital. So does that lone pair get counted towards the pi system? What do you guys think? To be counted in a pi system, it has to be in a p orbital, right? So this lone pair is not counted in the 4n plus 2 rule. So it does not count in 4n plus 2 rule. And this gets a little confusing because let's take another example where this other molecule looks very, very similar, but we're going to remove something out of it. This compound is called pyrrole. So it looks a lot like pyridine. We've just reduced the ring size, right? So instead of a 6-membered ring, we've got a 5-membered ring. And again, I'm going to try to draw this on the side. Okay. Let me try to clean this up a bit. That's about as artistic as I get. I apologize. And we'll go through and we'll draw in all these p orbitals. And then over here we also have hydrogen that's bound. All right, so those 2 back bonds, these CC bonds that are double bonds, they have pi bonds in them, right? So we can go through and we can say, all right, we've got shared electrons between these 2 pi bonds. Now where's the lone pair? Exactly. So if we look at the lone pair in this one, the lone pair is in the p orbital because the hydrogen is taking up that sp2 lobe. So in this example, the lone pair is in a p orbital. and it counts for the 4n plus 2 rule. So this one is aromatic. Both of them have 6 pi electrons. The difference between pyridine and pyrrole is pyridine has 6 pi electrons that are already due to the double bonds. So each double bond has 2 pi electrons. Where when we look at pyrrole, we've got 2 double bonds and 1 lone pair. So each double bond counts for 2, and the lone pair counts for the remaining 2. They both have 6 pi electrons. All right, now let's take this one step further and look at one that's even crazier. This was a molecule we actually saw on our quiz. This is furan. And again, I like to tilt these on the side and take a look at them that way. So I'm going to do carbon, 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 oxygen, carbon. Whoa. Let me clearly draw these. Right. And we'll draw in our p orbitals again. And I'm going to draw another orbital out here. So if we look at furan, those 2 back carbon bonds are pi bonded, at least using the representation we've drawn. So I'll label these 2. Those each count for 2 electrons each. But if we look at oxygen, it's got 2 lone pairs in it, right? Where's 1 lone pair? One will be in the p orbital, and where will the other one be? Yeah, exactly. So if we look at this one, you can say 1 lone pair is in the sp2 orbital. And then the other lone pair is in the p orbital. The p orbital. And so if we're counting our 4n plus 2 pi electrons, do we ever count sp2 orbital electrons? No, because these can't be delocalized through the p orbitals that are next to it, right? They don't line up right. But if we look at this p orbital, it does. So how many pi electrons are in furan? 6, exactly. So if we look at furan, it has 6 pi electrons. Does that mean it's aromatic? Yes. Exactly. So furan is one of these weird examples where it has 1 lone pair in a p orbital and another lone pair sticking out in an sp2 orbital, and that can be a little confusing. All right, let's take one other example because I really want to drive this home. And this is something that's been luckily helping me quite a bit lately. Let me make sure I draw it with the correct position for the double bonds. All right, this is histamine. Have you guys ever heard of histamine? Yeah, antihistamine. This is a very, very bioactive molecule. It's responsible for a lot of allergy responses and things like that. So if you ever take antihistamines, this is directly what it's related to. The question is this ring aromatic? And I'll include the other lone pair. I want you guys to think about that. How many 4n plus 2 pi electrons are there? So if we look at the pi bonds, these definitely count, right? They're always going to be in p orbitals. But we know lone pairs can be in a p orbital or they cannot be in a p orbital depending on the situation. So the question is which lone pairs are in p orbitals? Is the top nitrogen? Yes. Why do you guys say that? Exactly. The hydrogen that's bound to that top nitrogen is in the sp2 orbital, which means that lone pair can occupy a p orbital. So if we look at this one, this lone pair is in a p orbital. What about this lone pair? What's it in? It's in an sp2 orbital.
How do you distinguish the difference? Like, how do you just know that's in a p orbital and that's in a p?
That's a good question. So if we look at this lower nitrogen, it's got a p orbital sticking out, right? But this p orbital is occupied, right? It's occupied using this pi bond. So you can't have a lone pair in that p orbital if it's already full, which means it's got to be in an sp2 orbital.
And then the other one doesn't have a pi bond right next to it.
Exactly. Yeah. And anytime you can adjust the lone pair so that it contributes to resonance stabilization, it will, because that driving force is very, very strong. So even if you have a position that, like that top nitrogen, looks like an sp3 hybridized position, it will actually convert to an sp2 hybridized position in order to allow for resonance stabilization, because that's so favored. So it's very common to see these and then say, well, isn't that sp3? No, the top nitrogen is sp2 to allow for resonance to occur. So it can be a little confusing with some of these examples. Just like we saw with Perl. Perl was a good example of seeing that. If we look at the Perl nitrogen here, we would initially say, well, shouldn't this be sp3 hybridized? We'd say, well, not really. We'll actually convert to sp2 hybridized to allow this lone pair in the p orbital to be delocalized through the ring. That allows for resonance stabilization. Does that make sense? Yep. Okay. So let's switch gears a little bit and talk about how we can do chemistry on aromatic rings. We'll talk a lot more about this next term, but this term we're going to scratch the surface a little bit. And if we have a benzene ring with an alkyl group coming off of it, we have a very unique position on it. This position right there, that carbon coming off of the benzene ring, is called the benzylic position. Equals carbon coming off a benzene ring. And these carbons are very, very, very reactive. It can do quite a bit of chemistry, and we'll go through and talk about the chemistry we can do at this position, but all of these reagents, with the exception of one, we've already seen before. So let's think about oxidation chemistry. So let's say I've got an example here, and we've got a very simple benzylic system. Does anybody know the name of this benzene system? Toluene. So it's toluene? Yeah, it's not toluene. I know if you look at it, it looks like it should be pronounced toluene, but it's toluene. And this has an oxidation state of -3 for that carbon that's in the benzylic position, right? Because it's more polar than the hydrogens. It'll take both electrons from each of those sets. So that's 6. Then 1 electron from that carbon-carbon bond, that's 7. So 7 minus 4, or sorry, 4 minus 7 is -3. And then we can take this and we can oxidize it, and we can say, all right, let's change the oxidation state to this straight up to a carboxylic acid. So if we do this, the oxidation state changes to +3. So it's losing 6 electrons, right? So that matches our oxidation rules that we learned from Gen Chem. What reagents have we seen where we can oxidize things? Yeah, chromic acid. We saw that in the alcohol chapter, where if we have a primary alcohol, we can convert it to a carboxylic acid. This is really, really similar, right? But in this case, we're not using a primary alcohol. We're just using a benzylic carbon. So we can do Na2Cr2O7, that's sodium dichromate, sulfuric acid, and water, and you can get this reaction to go pretty easily. Another way of doing this reaction, too, that's actually more common is to do it in 2 steps. The first step, you do KMnO4, potassium permanganate, and you run this in water, and you heat it up. So it's KMnO4. Sorry, my handwriting's not great. And then in the second step, you can add acid. And the same reaction happens, and you avoid all of the nasty chromium products for the chromic acid reactions. And this one is usually preferred for doing benzylic oxidations, but it does the exact same transformation here. All right, let's take a look at another oxidation reaction. What if we have a tert-butyl group? And I react this with, oh, shoot. Oh, man. Cr2O7, sulfuric acid, and water. What will our product be? Won't happen, right? So if we look back in our alcohol notes, could we oxidize a tertiary alcohol? No, it's impossible, right? So same thing is true with benzylic positions. There is no reaction. Just like you can't have a reaction at a tertiary alcohol, this is a tertiary carbon, or quaternary carbon, I guess, and you can't oxidize it. It's just simply not possible. The other interesting reaction you can do with oxidation so let's say I've got this guy, and I do Na2Cr2O7, sulfuric acid, and water. What product will we get out of here? Carboxylic acid in the benzylic position. What happens to the rest of the chain? It just gets cleaved off. So in this case, you get the same product as we saw above, because the oxidation can only occur at this red carbon. It won't occur further down the chain because those aren't benzylic carbons. They're not the carbons that are attached to a benzene ring. The other 2 carbons, that ethyl group, just gets cleaved off. And so we're not worried about that. We're only oxidizing the benzylic position. Yep?
So is there any way to actually take off the carbon coming out of the benzene?
So to cleave off the benzylic position?
Yeah.
That gets into more advanced chemistry than we're going to cover in this course. But there are ways to do that. They're just usually involving radical reactions and things like that. Yeah, they're not easy reactions. Yep. All right, so we can do all sorts of unique oxidation chemistry. We've seen most of these reagents before. One reagent you've also seen before was in our... Sorry, did you have a question?
Yeah. So what if you have not a tertiary or a second? What if you have like a tertiary, like you have 2 branches off of it, not 3 or just 1 like that?
So you're saying, like, what if we have a group there?
Yeah, like another methyl group off of that.
Yep, or even like that?
No, like off of the red one?
Off of the red one?
Yeah.
It will cleave off any alkyl groups and only give you the benzoic acid group. So it doesn't matter what you have on there, it'll give you benzoic acid. If it's like this top one where you've got 3 alkyl groups coming off of it, then you're stuck. You can't get a benzoic acid there because you can't oxidize that.
So you're saying if there's some methyl hydrogen off the red dot, that would be tertiary position, right? Yeah.
Yep, so if you had a methyl group here, you could also get to that same product because we don't have a quaternary carbon in that position. You can still oxidize that twice.
There's still a hydrogen there.
Yeah, there's still a hydrogen there. Anytime you have a hydrogen on a benzylic position, you can oxidize it to your benzoic acid. That's a good question. All right, the other reactions we've seen that are very, very similar is the free radical bromination. So if you go back to the chapter on radical chemistry, we had a section where we could brominate allylic positions. if we look at benzene rings, specifically the benzylic carbon, they're kind of allylic. So if we look at this carbon here that I'll highlight in red, it's pretty allylic. It's the carbon right next to a double bond, but it's also benzylic. So benzylic is really a more, I'm trying to think of how to explain this. A benzylic group is more descriptive than saying allylic, because benzylic is specifically next to an aromatic ring, not just next to one double bond. So we can brominate this position. Does anybody remember the reagent that we need to do allylic brominations? NBS, exactly. So if we do this, we can brominate right there. And then we'll also get our enantiomer too, right? A radical won't favor one side over the other. And so we just need NBS. And we can do a radical initiator like light or heat. Usually with NBS, you just heat it up in order to initiate the formation of the radical. Do you guys remember the mechanism for radical reactions? Sure? No? I'm not hearing any overwhelming stuff, so we can continue on.
Let's go over it.
Go over it? All right. So I'll do the mechanism for this one. So what's the first step in any radical reaction? Initiation. So we take our NBS. And we pop off one electron to each side. So now we've got a nitrogen with a lone pair and a radical, plus our bromide radical. There we go. All right, the next step, step 2, will be our what? Even before propagation.
The extraction.
Yeah, the hydrogen abstraction here. So we can say, all right, now we've got a bromide radical. It can take one electron from a CH bond, and the other electron gets dumped onto the benzylic position. Oh, that should only be one dot for a radical. And then we form HBr. Why is this radical so stable even though it's secondary? Because of resonance, right? So just like with allylic radical reactions, they're resonance stabilized. This one's even more resonance stabilized. So this is a very, very stable radical, making this reaction incredibly regioselective. If you do NBS, are you going to brominate the ring at all? No, because of resonance stabilization. So bromination for this one will only occur at the benzylic site, not anywhere on the ring. Yep.
What do we call the second step? Like the first one was the initiation.
This is hydrogen abstraction.
Oh.
Yep. And then the next part is our propagation. So now that we've got our radical ready to go, this will actually react with trace bromine that's present in solution. So this radical will come over, this radical will go there, and then we'll recreate our bromide radical. So I'll do Br plus En because we know it can react from either position, and then we recreate our bromide radical. And then what's our last step now that we've created our product? Termination. So I'm just going to do Br dot reacting with Br dot in order to do our termination. And we end up just recreating our bromine that's used in the reaction. So this is an incredibly versatile reaction because as soon as we install a bromine in the benzylic position, what sorts of reactions can we do with it? A billion, yeah? So we've got a good leaving group. What can we do with good leaving groups? We can substitute them off. We can eliminate them. We can form double bonds. Once we have an alkene, we can convert it to an alkyne. We can convert it to an alcohol. We can do all sorts of crazy stuff going from this simple intermediate. So now we can start from a hydrocarbon that's aromatic and then build up from there. So let's briefly cover the substitution reactions that we can do. So hopefully these are review for you guys. So let's just say I've got bromine on there, and I want to put an alcohol on the benzylic position. What reagent do I need? Yeah, we can do sodium hydroxide. Is this SN1 or SN2? SN2. Why is it SN2 and not SN1? Yeah, it is a primary carbocation, but it can be stabilized by resonance. But let's think about that backside attack. Is that backside attack pretty accessible? Yeah. So it has more to do with the accessibility of the backside attack. And if we have hydroxide, it can easily access that backside, knock off the bromine, and then we install our alcohol. Just like with normal SN2 reactions, we'll also invert stereochemistry there. But it doesn't really matter here because there's no stereochemistry. What if we have bromine here, and I want to make an alcohol? What reagent would I need?
You just do the same thing.
So if we use sodium hydroxide, it wouldn't really work for backside attack. The backside attack's too crowded, so we can't do SN1.
Get elimination too.
Yeah, and you might get elimination too. So we need a weak nucleophile. What would a weak nucleophile be that could install an alcohol? Water, exactly. So you can do H2O and just do the SN1 reaction. And in particular, we said that there is a very, very stable intermediate. Because not only is that carbocation tertiary, but what else is going on? Resonance, right? So we can do SN1 or SN2 reactions on these depending on how hindered the backside attack is. If the backside attack is very hindered, SN1 is preferred. If it's not hindered and you have a strong nucleophile, you can do SN2 reactions, specifically if it's a primary electrophile. Same sort of trends hold true for elimination reactions for these. With elimination reactions, let's start with our alcohol that we just made. What reagents would we need in order to form a double bond? So if we did a strong base, we would just deprotonate our alcohol, we'd be stuck. All right, so one idea is do tosyl chloride and pyridine and then use a strong base. What would even be easier and greener than that? We did this in lab, where we had cyclohexanol and we created cyclohexene. Acid catalyzed dehydration would work really well for this. So you could do the tosylation and then strong base, but why do two steps when you can just drop an acid and heat it up, right? So I would just say H3O plus and heat, and this would be an E1 or E2 elimination. Be E1, because first we protonate our alcohol. The alcohol turns into a great leaving group and we can form a very stable carbocation. So this would be an example of an E1. Let's take a look at another example though, where it's slightly different. Let's say we already have a good leaving group and we still want to form this same product. Now what could we use? Any strong base, right? In this case, I would use a really strong base. I'm just going to arbitrarily pick sodium ethoxide because it's cheap. And then we can drive an E2 elimination reaction for benzylic positions in order to get our elimination product. Does that make sense? So this is all review from first term. Now where it starts to get interesting is with reduction reactions for these. So we already talked about oxidation. Let's say we've got styrene. And I want to go reduce that exterior double bond into a single bond. What reagents would I need?
Strong acid?
Not strong acid. H2, and then what do we normally use as our catalyst? Platinum or palladium. So I'll say H2, and then I'll say platinum. And in particular, let me move this over. When we do this reaction, we fill it up something called a par shaker. And this is a sealed vessel, and we can actually pressurize it with hydrogen gas. And typically when you do this, you do it at about 2 to 3 atm. That's a pretty reasonable amount of pressure. It's not a scary amount. You're not worried about it blowing up in your face. If we want to go even further, we can actually create a cyclohexane ring out of this. Same sort of idea applies. But do you think we need to add more or less hydrogen in terms of pressure? Quite a bit more. So not only do you need 3 equivalents of hydrogen, but this is typically done at around 100 atm. In order to do these reactions, you have to have very, very, very specialized equipment. Typically, you have to go to a big research lab, and normally they don't do these reactions synthetically because they're not very useful. But it's an interesting calorimetry experiment, and you can actually reduce a benzene ring to a cyclohexane ring. And typically, the catalyst that they use nowadays is a nickel catalyst rather than platinum or palladium. And then they really, really crank up the temperature for these.
Is it 3 hydrogens because there's 3 pi bonds?
Yeah, you need 3 equivalents because there's 3 pi bonds. So we're actually adding, in this one, 6 hydrogen atoms to the ring, which means we need to have 3 equivalents of H2 gas. So this first one is a gentle reduction. The second one is harsh. So just like with oxidations, we can have varying degrees of our oxidative power. Same thing with our reducing conditions. We can have very strongly reducing conditions and reducing conditions that won't touch a benzene ring. So that's very useful synthetically, especially if you want to only reduce alkenes and not an aromatic bond. All right, the last one, we're not going to cover the mechanism today, is called the Birch reduction. And we'll cover the mechanism tomorrow, but the Birch reduction is slightly different. We take a benzene ring, and we can actually just reduce part of it. And so now we've got an unconjugated system, and in order to do this, we use sodium metal, methanol, and then ammonia. And we'll cover this reaction tomorrow. But for the problem of the day, what I want you guys to do is start trying to utilize your synthetic toolbox again, get that back into the front part of your brain, and then work through this problem. Try to work in a group if you get stuck. It's a lot more fun to work through synthesis problems together rather than alone.